Hi, this video tutorial explains how to design logic gates using memristors in Hspice. I'm using 32nm FinFET technology. Memristor, which is the fourth circuit element, is a nonlinear resistor with memory. So, this curve here shows the ideal switching characteristics of memristor. This is basically simulated in Hspice, and this is the code for memristor model in Hspice. Let us run this code and check whether the characteristics are appropriate. Run your xmink, run your putty, log into your server, using your credentials. I created a folder called Memristor. Now, a Hspice file to check the characteristics should be created. Basically, name it as Memristor. .sp is the extension for the file. Copy the code and just right click on the editor to paste it. Dot option post, dot option measure digit is equal to 6 and dot temperature 27 are the default lines. Dot option post generally posts your results at the output. Dot option measure digit is equal to 6 means that the results will be with 6 digits after the decimal point, and the temperature is 27 degrees centigrade. This is the subcircuit for memristor with minus and plus as two nodes of the memristor. The subcircuit should be ended with dot ends and the name memristor. A voltage source of sine input is given with the name V in between the two nodes 0 and input. Now call the memristor. Mem is the name of the memristor, and the two input and the negative node. Memristor is the name of the subcircuit, and the transition analysis is performed between 0.1 milli to 10 milli. Probe is used to post the results, and dot end is used to end the Hspice code. Now close this editor. To close the editor, use Ctrl X. This asks to save, so press yes, give the name, press enter to save it. Now to run the Hspice code, give Hspice space the file name .sp. Use cscope to check the results. Now the cscope window will pop up. Open the signal manager. Open plot files. Memristor.tr0 is the transition which we performed. Open it. And Vin is the input sine wave. Now to check the IV characteristics, set the V to the x-axis. Select it and set. Plot the current. This graph shows the IV characteristics of the memristor model which I used, which is basically appropriate. Close this. Now a logic gate is designed using this memristor subcircuit. These are the results of the memristor subcircuit characteristics. Yeah. Now to create a NAND logic gate, I will create a file with the name nano AND gate .sp is the extension for Hspice. So basically, to write a Hspice code, you need to have the transistor level circuit, the technology which you would like to use, and the input pulse transitions, the model files, which are generally from the PTM website, predictive technology model, and the measurements which you would like to perform. This is my transistor level circuit, a 2-input AND gate with the memristors. The two A in and B in are the two inputs for the memristors, and the output will be given to an inverter. Basically works to get an output of AB, which is a logical AND. The technology file which I am using is the FinFET 32 nanometer technology. And for an AND gate, the input pulse transitions can be written as this is the truth table of an AND gate. To write the input pulse transitions, you generally go from 1 1 to 1 0 or 1 and then come back to 1 1 and then go to 0 1 and then come back to 1 1 and then go to 0 0 and come back to 1 1. These are the input transitions. Just follow this pattern to write the input transitions. A, B are the inputs. So the flow of the input transitions will be from input 1 1 to input 0 0 and then comes back to input 1 1 and then goes back to input 0 1. Similarly, write the complete input pulse transitions. This will be 1 1 to 0 0 to 1 1 to 0 1, 1 1 to 1 0 and then to 1 1. And then we need the model files. Download the PTM Download the model files from the PTM website. I'm using 32 nanometer FinFET technology, so I downloaded 32 nanometer FinFET technology model. And the measurements which I would like to perform are the time delay, average power, and the peak power, and the power delay product. So the first sentence of our Hspice code will be the name, which basically connects the Hspice code to the output C scope, Cosmoscope. And the dot option lines are used to post the outputs and the accuracy of the output measurements and the temperature, which I set to 27 degrees centigrade. And then we need to declare the parameters. I'm using parameters like VDD, power supply, and the pulse width, delay, and the length of my transition, which is 7 pulse widths. Now declare the transitions. So I'm performing a transition of from 10 pico to the length of transition, which is 7 into pulse widths. Then you can also perform transitions on your parameters like VDD and other parameters like width, length, etc. So to perform a transition on VDD, I would write transition from 10 pico to my length of tran with a sweep on VDD from 0.8 volts to 1.2 volts maximum with a step size of 0.05 volts. I'm commenting this out. Next, declare the parameters of length and width of your circuit, of the transistors used in your circuit. I'm using a 32 nanometer technology, so my length and width will be 32 nanometers. And then the VDD which you declared must be declared globally. So to declare the VDD as global, you use statements of the source VDD between the nodes VDD and 0 with a voltage of VDD which you declared previously. And I'm declaring this as global dot global and between the nodes VDD and 0. Then I'll write my input pulse transitions, which I already explained. Just copy and paste in this. My input pulse transitions will be input VA between the nodes AN and 0, piecewise linear. From at 0 pico, my input A is VDD till 1 pulse width it's VDD, and then at 1 pulse width plus delay it goes back to 0. So this is how you write the input pulse transitions. Next, you have to write the circuit description. So our circuit is something like this with 2 memristors, 2 inverters and a buffer. So instead of writing the complete circuit description, we can also use subcircuits in order to reduce the code length. So this how to write a subcircuit is shown here. I'm explaining the subcircuit for a regular NAND gate of CMOS NAND gate shown on your right side. AB are the inputs of the NAND gate, and this is the subcircuit of the NAND gate in FinFET using FinFET. So this is the XT1 is the name of the NAND transistor. NAND will be my drain. A is the gate. A is the gate again, and then the source. That means the FinFET transistor syntax will be name of the transistor, drain, gate, and source. So it's the PMOS, so I declare it as DG PMOS with a width of 2 into minimum width and length of minimum length. Similarly, write all the transistors. And to write a syntax for subcircuit, you generally use the syntax as dot subcircuit, name of the subcircuit which you would like to write. Let it be like inverter, NAND, NOR, etc. The inputs and the outputs. Write the circuit description here and end the subcircuit with dot ends. Though, and the syntax to call the subcircuit will be X and name any of the name which you would like, the inputs and the outputs, and the name of the subcircuit which you gave while declaring the subcircuit. So here is a basic example for the subcircuit inverter. So dot subcircuit subckt is the syntax, name of the inverter, input and my output. XP1 is my PMOS, FinFET PMOS, NP1 and XN1 is the FinFET NMOS. So this is my drain, gate, source, and DG NMOS, width and the length, and dot ends and your subcircuit. The circuit description for my circuit should include the memristor model as well because I'm using the memristor. So I'm adding my subcircuit for memristor which we checked previously. Now add your circuit description for the inverters and buffers which I use later. So I wrote the subcircuits for each and every inverter and the buffers used. So to call my memristor, I will give one of my memristor as x memristor1, which accepts the input as an and the output must be at f. So I'm calling the subcircuit memristor, so the name of my subcircuit is memristor, which I declared. Next, call memristor2 with input b underscore n and the output at f with memristor. So next, call the inverters and the buffers similarly. Next, I would like to measure power delay, so I'll add my measurement file to measure the average power. Dot measure transition average power from 0 nanoseconds to my length of time measures my average power. Similarly, write the measurement file for peak power. So to find the time delay, you have to find the maximum of the time delays for all the transitions. So dot measure transition C1 is the time delay calculated while triggering VA underscore N is my input in. When the input goes to VDD by 2, 50% of my VDD at a time of nanoseconds, the input has a fall, so fall is equal to 1, and the target, that is my AND output, is calculated at 50%, which is a fall, so fall must be active. Similarly, find the time delays at all the transition. So to find the time delay of the whole circuit, you must find the maximum of the time delays at each and every transition. So to find the maximum, I'll write a code which helps me find the maximum of the time delays. So the maximum time delay is given as TD, and then find the power delay product. I'm finding the power delay product, so dot measure for the transition which I'm running. The power delay product is my parameter, and the parameter must be equal to time delay into my average power. So our code is complete, and then we have to add our model files. So here is my model file for 32 nanometer FinFET. Just copy and paste your model file, or you can directly sync it into your server. So to end your model file, use dot ends, basically because it's a subcircuit, and to end your Hspice code, end it with dot end. And to close your Hspice, press Ctrl X, save the modified changes and give it a name, press enter. To run your Hspice code, give Hspice space name of the file and .sp. Now my job has concluded, and then to check my results, I go to Cosmoscope, so it's a C scope, and enter. Will open your Cosmoscope. Signal Manager, open plot files, AND gate, open. My output is AND buffer. Before the buffer, my output is AND, and my inputs are in and being. You can check my outputs of AND gate using memristors. So inputs A and B are high, so my output is high. Inputs A and B are low, my output is low. Any one of the input is high, my output is low. You can see it here, A is 0 and B is high, my output is low. Okay, so the functionality is right. Close your C scope. And the time delay will be shown here while you run your Hspice. The time delay of my circuit is 9.4 picoseconds and the power delay product is 269.46 picojoules. And the average power is shown here, which is 28.56 watt, and the peak power is shown here, which is 100.0 watts. So now to sweep your VDD, go back to your code, sweep your VDD using a transition from 10 pico to the length of the trans. I'm sweeping my VDD from 0.8 volts to a maximum of 1.2 volts with a step size of 0.05 volts. And so it must start with .trans. Close your code, save with name. Then to run your code, give a command hspice space name.sp. So this sweeps my VDD and runs my code for all the VDD with a step size of 0.05 volts. Now to check the results, give the command cscope, which opens your Cosmoscope. To check the graphs of PDP and the time delay or the power, go to Hspice measure and select your measurement, click open, and then set your x-axis to VDD, set, then plot the time delay. My time delay parameter is TD, my time delay plot, this is my PDP. So these are the results of my AND gate using memristors. These are the results of my AND gate, and thank you.